Sometimes in a double replacement reaction, you mix two solutions together and it produces a compound as a product that just won't dissolve in water. Here's an example. If I had a solution of lead 2 nitrate, PbNO32, and I mixed it with a solution of potassium iodide, here's what would happen. I would get some potassium nitrate, KNO3, and that would dissolve in water. That would be aqueous. But my second product would be lead 2 iodide, PbI2. Well, PbI2 doesn't dissolve in water. It shows up as this yellowish precipitate, it's called. A solid that forms when two solutions are mixed together is called a precipitate. Here's another example. If I had an aqueous solution, a dissolved in water solution of silver nitrate and sodium chloride, here would be the results. Again, you're taking the outside two and the inside two. So one of the products would be NaNO3. That turns out to be aqueous. That dissolves in water. The outside two species, the Ag and the Cl, would go together 1 to 1 because silver is 1 plus and chlorine is 1 minus, but that doesn't dissolve in water. That's a solid. That's a precipitate. Of course, predicting whether or not a precipitate is going to form is going to require that we understand some things about what dissolves in water and what doesn't dissolve in water. And we're going to look at 3 terms here, and then we're going to look at some rules for applying these 3 terms. One term is called solubility. Another way to describe solubility is just dissolvability. Dissolvability. How well does it dissolve? Things with high solubility dissolve really well. The word soluble means dissolves easily. If something is said to be highly soluble, that means you put it in water and it's pretty much always going to dissolve. Now here's what dissolve means. For an ionic compound, like let's say sodium chloride, which is pretty soluble, when I put it in water, this solid, table salt, splits up into sodium ions and chloride ions, individual ions in water. Because these are dissolved in water and they're atom-sized, you can't see them anymore. You can see crystals of salt. Those are very large collections of atoms. But individual atoms in water, you can't distinguish them from the water, and so it's a homogeneous mixture. That's what it means for something to be soluble if it's an ionic compound. Insoluble, well, the prefix in means not. So not soluble means doesn't dissolve in water very well. So if something is said to be insoluble, that means it's not going to dissolve. Here's an example of something like that. Copper 2 hydroxide. If I put this in water as a solid, nothing happens. It's going to stay there. It's just going to sit there as a block or a puddle of crystals of copper hydroxide. It's not going to split up into ions very much at all. Highly insoluble. So in order to be able to apply this, we need to have a set of rules. And these rules are going to seem like a lot of rules to memorize, but they boil down to something that's usually fairly small set of knowledge. One solubility rule that's very common, very useful, you're going to use this one a lot, says that all group 1 metals or ammonium ion are highly soluble. So that means any of the metals in this column right here, that starts with lithium, sodium, that group there, and then this ammonium ion, NH4+. If those are the cation, it really doesn't matter what the anion is, it's going to be highly soluble. Here's an example. K2S, highly soluble because it's a group 1 cation. So when you put that in water, it's going to split up to K pluses and S2 minus ions. Or sodium chloride, table salt. That splits up to sodium ions and chloride ions, as we've seen. And here's another one, ammonium chloride, NH4Cl. Put that in water, it's going to split up into ammonium ions and chloride ions. Highly soluble if it's a group 1 or an ammonium. Another rule, this involves anions, is nitrates and acetates are highly soluble. So, for example, if I had iron 3 nitrate, if I put that in water, it's going to split up and give me iron 3 ions, and it's going to give me some nitrate ions too in aqueous solution. Highly soluble. Or if I had nickel 2 acetate, if I put that in water, I'm going to get nickel 2 ions, and I'm going to get acetate ions. Now I'm not bothering to balance these, but they could be balanced. Another rule that has exceptions, it's not an all-the-time rule, is chloride, bromide, or iodide. These are called the lower halides. So these are the halogens, chlorine, bromine, iodine, right there. When those are the anion, it's usually soluble. In compounds in which chlorine, bromine, or iodine are the anion, it's usually soluble, except when the cation happens to be Ag+, lead 2+, or a polyatomic cation called Hg2 2+, mercury 1, that's called. If those are the cations, well, then it's not going to be soluble. So, for example, if I had iron 3 chloride, FeCl3, that's not one of my exceptions, so I put that in water, it's going to split up to iron 3 ions and chloride ions. But if I had AgCl, put that in water, nothing happens, because silver is one of our exceptions to the solubility of lower halides. If the anion is sulfate, SO42-, most of the time that's highly soluble. In other words, it'll dissolve, except in 3 cases. One of the exceptions is, just like for the lower halides, lead 2. Another one is barium 2+. And a third exception is calcium 2+. If those are the cations, then it's not soluble, but it'll be highly soluble with other cations. So, for example, if I add iron 2 sulfate, FeSO4, that's going to split up and give me iron 2 ions and sulfate ions if I put it in water. But if I have barium sulfate in water, it doesn't dissolve. Another common rule, if your anion is hydroxide, the OH- ion, it's almost always insoluble. Most of the time you're going to see hydroxides that are either group 1s or transition metals. Group 1s are going to be soluble with hydroxide. There are 3 other things that are soluble with hydroxide, and that's calcium, strontium, and barium. Calcium, strontium, barium. If those are the cations, then it'll be soluble. Any transition metal will not be soluble. The rest of the alkaline earth metals will not be soluble. Aluminum hydroxide will not be soluble. The only ones that are soluble with hydroxide are group 1s, calcium, strontium, and barium. If the anion is carbonate or phosphate or sulfide, those will almost always be insoluble. In other words, they won't dissolve in water. They'll always make precipitates, except the things that never make precipitates for cations. And that would be your group 1 metals and ammonium. So, for example, if I had iron 2 sulfide and I put that in water, sulfides are almost never soluble, and so nothing would happen. But if I had sodium sulfide, Na2S, this is one of the few exceptions in which it would dissolve, because sodium is a group 1, and that would give me ions in solution. Now, once you know about these solubility rules, you have the ability to make decisions about if a precipitate is going to form or not. So the first thing you want to do is look at the reactants. Find out what ions are present in a solution mixture. So imagine the ionic compounds that are being mixed together, splitting up into cations and anions, and just find out what cations and anions are there. So let's say we were doing this one. NaCl, aqueous, reacting with AgNO3, aqueous. As I approach trying to predict the products here, I want to split this up into ions and just make a list of what's there in my mind or actually on paper. Na+ is going to be in there. Sodium chloride is also going to give me Cl- ions. Ag+ is going to be in there, and nitrate ions. That's my list. The next thing I want to do is switch up the cations and anions. Repair them only the opposite way. Put the inside 2 species together and the outside 2 species together and figure out what the possible products are. Well, in this case, the inside 2 would give me AgCl. The outside 2 would give me NaNO3. And the last thing to do is, if one or more of the products is insoluble, a precipitate will form. Otherwise, it's just a no reaction. So in this case, I take a look at my two possible products that might be produced. Sodium nitrate is not going to be a precipitate because compounds with group 1 cations are always soluble, and compounds with nitrate as an anion are always soluble. Now if I look at AgCl, this is a lower halide. Chloride, bromine, and iodine ions are in compounds that are usually soluble. There are 3 exceptions. Silver is one of them. So this will be a precipitate, and we will have a reaction. So I might write my reaction this way. NaCl aqueous and AgNO3 aqueous are going to react to form 2 products. The first one is sodium nitrate. That is soluble, we found. And the second one is AgCl, silver chloride. And that's not soluble, that's a solid. So there's my precipitate. Let's try another example. Here's lead-2 nitrate with potassium iodide. So I'm going to look at what ions are there. I've got Pb2 plus here. I've got nitrate, NO3 minus. I've got potassium, 1 plus, and I have an iodine ion. Group 1s are always soluble. Nitrates are always soluble. So when I pair these two together, I'm going to have something that dissolves in water. KNO3 aqueous. But when I pair these two together, I have a lower halide with one of its exceptions for solubility. Lower halides are always soluble except with silver, lead-2, and mercury-1. And here's lead-2. So that means I'm going to get a solid. I'm going to get an insoluble compound. PbI2 will be a solid in this compound. Again, I'm not balancing, but you certainly should try and balance if you're asked to do so. Let's take a look at this guy. He's going to do the reaction that we just did. He's going to mix lead nitrate with potassium iodide. He's got his solution of lead-2 nitrate in the test tube, and he adds the potassium iodide. And that lead-2 iodide is the yellow precipitate. Let's try another one. Sodium nitrate and calcium hydroxide. Looking at the ions that we have present, we have sodium, which is a group 1. That's going to be soluble with any anion. Nitrate. Well, nitrate is an anion that's soluble with any cation. We're going to have calcium 2 plus. And we're going to have hydroxide 1 minus. Calcium is insoluble with most things. But when I pair it up with the sodium from the other compound, it's going to be soluble because group 1s are always soluble. Calcium precipitates with some things, but not with nitrate, because nitrate compounds are always soluble. So since we don't get any precipitate here, we have an aqueous and an aqueous. This really is no reaction. So I'd write down no reaction. Here's why it's no reaction. Because NaNO3 aqueous is really sodium ions and nitrate ions. Calcium hydroxide aqueous is really calcium ions and hydroxide ions in solution. After the reaction's done, I still have the same stuff. Sodium ions, nitrate ions, calcium ions, and hydroxide ions. They're just all floating around in the container just like they were before. Nothing happened. It's a no reaction. You try this one. Okay, here's your answer. The species that I have present are silver and chlorine, silver and chloride, and calcium and nitrate. When I pair silver with chloride, I'm going to get insoluble AgCl. So that's a precipitate. When I pair calcium with nitrate, I will get soluble calcium nitrate. Calcium nitrate is soluble because all nitrates are soluble. So that's an aqueous. So our precipitate is silver chloride in this reaction. Try this one. Okay, here are your combinations. The outside two would be iron with hydroxide. And this is iron 2 here because it takes 2 nitrates to satisfy it. So one of the products is going to be iron 2 hydroxide. Iron 2 hydroxide is going to be a solid. It's going to be a precipitate. It's not soluble. Remember, most hydroxides are not soluble. NaNO3, well, that's a group 1, which is always soluble with any anion, and nitrate, which is always soluble with any cation. So NaNO3 will dissolve in water. Try this one. Here are our pairings. If I pair barium with sulfate, I have an insoluble. Sulfate's soluble with most things, but not with barium. So barium sulfate is a solid. That's one of our products. My other combination would be copper 2 with hydroxide. Well, hydroxides are usually not soluble, except a few exceptions, and copper isn't one of them. So copper 2 hydroxide is also a solid. So in this case, we have two precipitates. Doesn't happen too often, but it happened here.